All right, what up, people? Today I want to discuss some applications that are tied to eigen-decomposition. In the previous video, we found the eigenvalues and eigenvectors of n by n matrix. In this case, we define it as A. And so now I want to show, okay, we could do the eigen-decomposition. So what other purpose does it have? So let's consider matrix multiplication. All right. So let's say you're interested in doing a square. All right. So a squared is just a times a, right? But let's define, remember that this guy is equal to a, right? So then you have two of those, so that's equal to a. And then right here, you have q inverse times q. Well, that's just equal to the identity matrix. And so we can rewrite this guy, this term, the Q and the Q inverse absorbs, and you're left with this expression right here. Well, capital lambda times capital lambda is lambda squared. And now we can rewrite our a squared as this expression right here. Now, if we were interested in doing a cubed, we, we can follow the same procedure. We can say that, well, a cubed is just a squared times a, and then we know that this guy is equal to a squared from this expression up here, and then this is equal to a. Well, once again, you have q inverse is equal to q, and that's equal to the identity. So now that you do all the multiplications, reduce, you have that a cubed is equal to this guy, q times lambda cubed times q inverse. And then you can do matrix multiplication to numbers as big as possible. The only thing you have to consider is whatever power that you have up here, you multiply it by uh, this your eigenvalues terms. And so we can create a general expression and saying if your matrix is decomposable using eigen-decomposition, you can do matrix multiplication using, this formula that you have right here. Um, yeah. So that's one application. And then another thing would be finding the matrix exponential of a matrix. So let's consider the Taylor series for e to the x. All right. If you don't know where this comes from, I mean, you can look it up from a formula from a book, but let's just say you know that the e to the x can be represented in the Taylor series. Now, if you wanted to find if we would replace the x term with a matrix in place for x, you get this expression right here. All we did is take away x and plug in a. But remember that a is equal to q lambda inverse, right? How about if we substitute that into our Taylor series expansion? So we plug it in. So remember that a is equal to that. We plug it in and we get this expression right here. Since we're dealing with matrices, a set of one, this would be the identity matrix. And we can substitute Q and Q inverse for the identity. I mean, whenever you multiply it, it will be the same, right? It'll still be the identity matrix. So I want you to see what these expressions have in common. They all have Q, Q, Q on the left-hand side, and Q inverse, Q inverse, Q inverse on the right-hand side of the expression. So we can factor out a q from the left and factor out a q inverse to the right, and we're left with the following Taylor series. So just imagine if we were to factor these guys back in and this back in to the left and right, you get this expression right here. But now we have this expression inside the Taylor series, and we can rewrite that as e to the lambda, right? And so now we have an expression for e to the a. So e to the a can be expressed as q times e to the lambda q inverse. Okay, so maybe the theory is a little bit confusing, but let's have an example right here. So in our previous video, we had that matrix A followed this. We did eigen-decomposition and we found out what our Q and our capital lambda is, right? So now we're interested in finding the matrix exponential of matrix A. And we already know what Q is. We know what Q inverse is. We have to figure out what E capital lambda is. All right. So with matrices, it's pretty easy. So all you do is just put E to the whatever number whenever it's a diagonal, right? So you do some algebra. So remember, this is Q, this is Q, this is Q inverse, and this is E to the capital lambda. And then, yeah, and then this is your expression right here. So this guy is E to the A. And let's say you had MATLAB. You cannot just say E to, or the exponential to the A in MATLAB. The particular function that it would be the exponential of a matrix, and then you would put A. And if you do that using the A matrix as that we defined above, you should get this. All right, guys, let's do a quick summary. So this video is based off two parts. If you want to do matrix multiplication and you know the eigen-decomposition, you're able to do a general expression for matrix multiplication using this guy. So whatever the power is, you multiply the capital lambda to that power, and it's easy because it's a diagonal matrix, and multiply it by Q. And over here, we use the Taylor series expansion to show that e to the a, the exponential of a matrix, is the same as q e to the capital lambda q inverse. And we have, so don't do this in MATLAB. I recommend using the exponential, and this m is for the matrix function. All right, guys, so if you have any questions, feel free to leave anything in the comments. Maybe I can make another video to clear things up if I can help out anymore. All right, bye.